Hi, everybody. I'd love to introduce Valerie Trouet from University of Arizona, and she's been using tree rings and like biological data like that to map out the history of the planet and climate change. Welcome, Valerie.
Thank you very much, Greg, and thank you very much for having me. I hope you can see my screen. I'm a professor at the University of Arizona, and I am in the laboratory of tree ring research. So we are a department of our own. We're about 10 faculty who all study the rings in trees, and my main research interest is using the rings in trees to study the climate of the past. So I'm a paleoclimatologist. And of course, nowadays, with ongoing anthropogenic climate change, a key question to ask oneself is why study climate history or the climate of the past in the first place? And my favorite way of explaining this is actually not based on tree rings. It's based on ice core data that you see here. So you're going to see quite a few of these graphs today, and it will always be time on the horizontal axis with the present to your right. So in this case, you're looking at 800,000 years with the present on your right, 800,000 years ago on your left. And the red line that you see is the amount of carbon dioxide in the atmosphere over those 800,000 years. And the black line underneath it is the temperature in the Antarctic over that same period. And so these data are derived from ice cores in the Antarctic. If you drill into the Antarctic ice for about a kilometer, the ice that you encounter is 800,000 years old. You can then pull that entire ice core, kilometer-long ice core out of the ice, divvy it up in millimeter thin sections, and so get an idea from 800,000 years ago till now. And actually, that ice still contains air bubbles of air that's 800,000 years old. And you can measure the amount of carbon dioxide in that air of 800,000 years ago up until the present. That's how you get the CO2 curve that you see. Won't go into too much detail, but there's some broad conclusions that you can draw from this graph. One is that neither the amount of CO2 nor the temperature on Earth have been a constant over time, right? There've always been fluctuations in the amount of CO2. They're very low frequency, so very slow fluctuations, but the amount of CO2 has not been constant, neither has the temperature on Earth. Two, the two co-vary with each other. When the amount of CO2 goes up, the temperature goes up. When the amount of CO2 goes down, the temperature goes down. That's the greenhouse gas effect in action that we know very well. The third important component is if you look at the numbers on the vertical axis for the amount of CO2, you can see that over the past 800,000 years, the amount of CO2 has varied roughly between 200 and 300 parts per million. So 200 to 300 parts of molecules of CO2 per air volume. And importantly, it's never been over 300 parts per million. So when I speak to a broad audience live, this is when I ask the question, does anybody have any idea at how much ppm, parts per million CO2 we are today? I guess here I'll answer the question myself. I looked it up this morning, and we are at 427 parts per million. So if you draw that line, if you add it to the graph I just showed earlier for the amount of carbon dioxide over the past 800,000 years, this is how far out of how unprecedented the amount of CO2 in the atmosphere is where we're at today. The graph you're seeing is from 3 years ago when we were still at 417. We've added 10 ppm just in the past 3 years. So this is a good way to demonstrate why it is important to look at the past, the climate of the past, the Earth's history, to understand what we're experiencing today and what the potential consequences could be. Of course, if you know that the amount of CO2 and the temperature on Earth covariate and have done so over the past 800,000 years, it's no surprise that we're running into record after record temperature-wise. So this is a map from Copernicus, European Climate Service Office, that showed that the summer of 2024 was the hottest on record, and by record they mean now instrumental record, globally, but also specifically in Europe. But I'm showing this map because I'd like, it'll come back later in the talk. So this is the heat map of the past summer of 2024 over here. To study the climate of the past, I've already talked, we have various, we use various geological and biological archives to do so. Already talked about ice cores. They can go back 800,000 years. We can use lake sediments, stalagmites, documentary data, pollen data, and so forth. My field of expertise, as I mentioned before, are the rings in trees, because trees form a ring each and every year, and how wide that ring is to a large extent depends on how good or bad the climate was in the year that that ring was formed. We can use these rings in trees to study the climate of the past, to reconstruct past climatic conditions. Now, of course, we are limited to some extent by the age of the tree, so we cannot go back 800,000 years like we can do with ice cores. But the advantage of tree rings is you can find them in very many places across the Earth's surface. So you can reconstruct the climate in many places. And another advantage is that, you know, because you have a ring each and every year, you can have very precise, you can reconstruct the climate for a specific year. Whereas with ice cores, you know, you can go back 800,000 years, but you don't have a data point each and every year of those 800,000. I mentioned that we're limited a little bit by the age of the trees. Luckily, that's not too limiting. The oldest living tree grows, it's a bristlecone pine. It grows on the boundary between, in the White Mountains, on the boundary between California and Nevada. And when it was scored, it was more than 5,000 years old in 2012. So that's and there's many bristlecone trees that are more than 4,000 years old. So they're, you know, started growing when we were building pyramids, and they're still growing today. It's quite remarkable. Of course, really important and really quick, if we want to study these ancient trees, like the bristlecones, like the giant sequoias, and many of these old trees, we don't need to cut them down to be able to study their rings. We use this tool. It's a hollow increment corer. You core it by hand into the tree. You extract what you see there is a pencil-sized sample from the tree. It doesn't damage the tree. It doesn't hurt the tree. It's really a small, like a quarter of an inch wide of a sample that you take. These samples then you bring back to the lab. That's where you sand them all. And when they're sanded, this is when the tree ring pattern comes out. And then you can start doing the actual work. One last big advantage that I'll talk about of tree rings is that we're not limited to living trees alone. So we can extract these data, these tree ring data from, you know, any kind of wood that has enough rings in it. That can be from dead trees, trees that died 400, 500, 1,000 years ago. Can be wood from historical buildings, can be wood from archeological sites. So tree rings have dendrochronology has an important application in archeology to date to the exact year when archeological sites were built. And even subfossil wood, so wood that fell into rivers or into lakes thousands of years ago, we can date and then also use that for tree ring reconstruction. And so by putting all of these sources together, the longest tree ring chronology that we've developed so far is the German oak and pine chronology, is 12,650 years old. So that is, for each of those 12,650 years, we have an exactly dated ring. So it's a continuous series.
So question, to what extent does the tree species matter, and how much has their growth changed? I mean, species evolve over that to 12,000 years. How much has it changed?
Species don't really evolve that much over 12,000 years. Where they grow evolves. Of course, there's, how it has changed is an important factor. I mean, I think what this is, as I mentioned, is the German. So this is specifically, this chronology specifically for Germany is based on oak and pine trees. And the way we, you can see it on the graph there, the way we can exactly date this subfossil wood, this archaeological wood, is that you match the ring patterns that you see in living trees. So a tree that grew, for instance, over the past 300 years, you have a ring pattern of how wide and how narrow the ring was in each of these years. So you have kind of a barcode of this tree's lifespan. And then you can match the wood that you find from a dead tree, for instance, a tree that died 100 years ago. And what we do is we pattern match the barcode that we find in the living tree with that we find in the dead tree. And if there's enough rings, there's only one spot where the two patterns will match. And that's how we get an exact date, because all trees that live in the same area in the same time, they're all subject to the same climate. And so they will all experience good years and bad years, and record that in their rings in the same way. Now, when I say all trees in that respect, this species dependent. Of course, some tree species are more sensitive to drought, where others are more sensitive to temperature and so forth. So some tree species, the most tree ring chronologies are specific for are species specific, so are based on one species, and all of them are location or region specific. So we don't have one global tree ring chronology. It doesn't work that way. Hope that answers the question in a nutshell.
Yeah, thank you very much.
Thank you. So the main applications of tree rings are climate history, would to study the history of climate. What my field of expertise is, as I mentioned, really important application in the study of human history, of archaeology, art history, and so forth. And then thirdly, of course, we're working with trees, so we're also able to look into the history of forests and wildfires, for instance. So I'll talk about these three applications for the rest of the talk. First one, I'll be very short. It's not my field of expertise, but I find it a really fascinating application. That's a study of human history. And one example is what you see here. This is the Miraflores triptych from a Flemish primitive, Rogier van der Weide, who lived from 1400 to 1465. That was his lifespan. Now, many of these medieval artists, they painted on oak wood panels. So the panels on which this triptych is painted are made of oak wood. And this triptych, there's two versions of it. There's two copies of it. One is hanging in the partly in the Metropolitan Museum in New York, and partly in Granada, and the other one is in Berlin. And so from art historical perspective, it was always assumed that the copy that was in the Metropolitan Museum was the original, painted by van der Weide himself, and that the copy hanging in Berlin was a valuable copy, also probably medieval, but nevertheless not painted by himself, but by someone who followed his school soon after. Now, dendrochronologists got their hands on or were involved in in using the rings in those that we can see on those oak panels to provide an exact date of when these the trees on which these oak panels were from which they were cut, from which these panels were made, when the trees were cut. And so the trees of the Berlin copy, the most recent ring they found was dated in 1424. So early in van der Weyde's lifespan, remember he lived from 1400 to 1465, early in his lifespan, but within his lifespan. So this is not proof that he painted it, but at least it's possible that he painted it. The copy that was hanging in the Metropolitan Museum in New York, however, the most recent ring on that oak panel, they date it to 1492. So that means that the tree from which these oak panels were made was still alive almost 30 years after van der Weyde passed away. So there's no way that van der Weyde could have painted this himself because the tree was still alive at that point. So this is proof that the MoMA, the Metropolitan Museum copy was actually a valuable copy, but not the original. So that kind of shook up the art historical world. An example of climate history, one study we did a few years ago in 2015 is where we used the rings of these trees. Well, I'll show it in a second. The blue oaks growing in the Central Valley of California to reconstruct the snowpack of the Sierra Nevada mountains. I don't know if there's anyone from California, but 2015 in California was in the midst of a prolonged drought that lasted from 2012 to 2017. And 2015 was particularly dire, and especially the snowpack in the Sierra Nevada mountains. What you see here are two satellite images of that snowpack in the Sierra Nevada mountains on your left. And so they're taken at the same time of year, end of late March, which is a good time to evaluate the snowpack because most of the snow has fallen at that point of time, but it hasn't melted yet. So it's a good idea to get an idea of how much snow has fallen over the previous winter season. On the left, you see the snowpack in a very average year, 2010. This is what what you can expect in a healthy snowpack in the Sierra Nevada mountains. On the right, same time of year, you can see what the snowpack was like in 2015. And so even from space, you can see just how little snow there was. And so again, this is at the end of the wet season in California. At that point, you can expect that there's not much snow that's going to still fall. So these were dire circumstances. And it was also all over the news. April 1st, 2015, many of the newspapers were reporting how there was so little snow in the Sierra Nevada that it was the lowest snowpack level that they had ever had since they started measuring snowpack in the Sierra Nevada, which was 80 years earlier in the 1930s. So when we heard this in my lab, and we heard that they were comparing this 2015 snowpack over the 80-year instrumental period, we realized that we could do better than that. We're tree ring scientists. 80 years is not. We're not very impressed by that. So we used these trees, which are the blue oaks. They live to be about 500 years old. They grow in the Central Valley in California, and they're extremely drought sensitive. There's not a dry year in California that goes by or that each and every one of these blue oaks forms a really narrow ring. They're some of the best recorders of drought that I know of, that I've ever worked with worldwide. As I mentioned, they can grow to be about 500 years old. So we use the rings in these blue oaks. We use a network of about 30 sites throughout the Central Valley, blue oak sites, to reconstruct the snowpack, not just over the past 80 years. So that's the red line that you see is the instrumental measurements of the snowpack. but now over the past 500 years. And so again, this graph shows on the horizontal axis time with the present on the right, 500 years ago on the left, and then the vertical axis in this case is the snowpack per year in the Sierra Nevada mountains. The dashed red line that you see is the snowpack level in 2015, and so if you compare the dark red line with the black line with the reconstruction, you can see that the 2015 low was not just a record over the past 80 years, but actually over the past 500 years, there had never been as little snow in the Sierra Nevada mountains as there was in 2015. This kind of made big news. It's very gratifying as a tree ring scientist to see your research covered in major newspapers and CNN and so forth. The reason why I'm showing this headline, however, is you can see our paper came out. We wrote it really quick. Our paper came out still in September 2015, so when this drought was still very much ongoing. And the reason why I'm showing is that in the same web page, they're talking about major California wildfires that were very much out of control. So that brings me to the next topic that we can study using tree rings, which is fire history. Again, we're going to look at California. Most of you are probably aware that in recent years, not just California, but the entire American West is struggling with increased annual area burn. In California, over the past 50 years, you can see the graph here, annual area burn has increased fivefold. And so, of course, that's related to anthropogenic climate change, hotter droughts, more droughts, longer fire season. That all contributes to an increase in wildfire. But that's not the only part of the story. There's more to the story than that. And the other part of the story is exactly what we can study using tree rings. The kind of fire that you see in this photograph is a ground fire. It's a fire that, as the name says itself, it typically stays close to the ground. It will burn your underbrush and your grasses, but it will typically never get big enough to reach the crowns of the tree. So it might clean out a forest, but it won't destroy a forest. And these are the fires that we can study using tree rings. When a fire like that hits a mature tree, it might wound the tree. It won't kill the tree, but it might wound the tree. And you can, if you walk through the Sierra Nevada or really any Western U.S. forest, you'll see trees that have these kind of fire scars in them. And these trees can be hit by subsequent fires if they're not destructive, if they're ground fires. They can record multiple fires in their tree rings. And so by taking, you can see a sample that we took out of a tree that was scarred by subsequent fires here. This kind of work you do need to do with a chainsaw. You can't, it's very hard to do with a cord, but you don't need to cut down a tree. It's not beautiful, but it doesn't hurt the tree all that much to take a sample out of it. When you take this kind of sample out of the tree, what you see is something like this. So this is a tree that was cut in 1998, or sample that was cut in 1998. And you can see all the fire scars that it has in it. So this tree had survived 14 ground fires between 1765 and 1889. So by looking at the, you can date each ring of the sample, and then you can date the ring in which each of these fires occurred. So you can get an exact year for when each of these fires occurred. Now you can do this, obviously we don't do this on one tree. We collect very many samples. This was what I did for a postdoc when I was working at Penn State, was to collect tree ring fire scar samples across 29 sites across the entire Sierra Nevada mountains, from Sequoia Kings Canyon in the south all the way to almost to Lassen in the north. And so we collected 2,000 wood samples. I dated about 20,000, almost 20,000 fire scars. When you put all of that together, you combine all of that into one big fat fire scar chronology, you can find which years are the years when the Sierra Nevada were the big fire years in the Sierra Nevada mountains. So by doing that, we put together a chronology from 1500 to 1900, and these are the big. So 1829 is this peak, for instance, that you see when 25 of the 29 sites that we sampled were all burning. Again, this is from all the way in the south to all the way in the north of the Sierra Nevada mountains. It doesn't mean that this was one big continuous fire, of course. It just means that the conditions were such that the fire risk in that year was particularly high, and there was a lot of fires happening simultaneously. You can then compare this fire chronology, which is really independent from the kind of drought reconstructions the snowpack reconstruction that I showed earlier. You can compare the fire chronology to drought reconstructions from the same region. And when you do that, you kind of see a bullseye over California, meaning that the fire years in California were the years that were also the driest years. So that, to be honest, I dated 20,000 fire scars to discover that when it was dry, it burned in California. So that was not the most novel takeaway from the study that we did. We knew that drought and wildfire were related, obviously, before we did this study. So we started digging a little further to see what else was there in our fire record, and I won't tell the whole story here. But one thing we found is these shifts. So again, here you can see again our fire chronology up until 1900, now with a 20th century fire record, so instrumental fire record merged with it. And you can see three distinct shifts in the fire regime, one in 1776, one in 1865, and then the most recent one in 1904. We don't find these shifts in the drought record or in any of the climate records. So these shifts are not related to climatic shifts. And the one I will refer to here is the most recent one, the one in 1904. And that's actually a pretty well documented event in Western US fire history. It's called the Smokey the Bear effect. So in the early 20th century, the US Forest Service was established in 1907 with the mission to protect Western forests to protect them in general, which included protecting them from wildfires. At this point in the early 1900s, they didn't know what we know now, that actually, these ground fires that clear out the forest every 10 years are a natural part of forest ecosystem. And so they didn't know that. They started putting out all the fires, hence the Smokey the Bear effect, and they were quite efficient at it. So since the early 20th century, for about a century, we've been very good at putting out fires, at fire suppression. And obviously that has an effect on your fire regime. Your fires are reduced, but it also has an effect on your forest structure. And so you can already see the Smokey Bear effect just in the sample that I showed before. So the sample was cut in 1998. Between 1765 and 1889, there was a ground fire that went through this forest, but didn't kill the trees, just about every 5 to 10 years, right? 14 fires in 120 years. That's every 5 to 10 years, there's a ground fire that would come through this forest and that would clean out the forest, that would clean out the underbrush and would clean out the grasses. But then between 1889, that's when the last ground fire is recorded, and then nothing until the sample was cut in 1998. So even just looking at the sample and seeing how much biomass this tree has added over the past century, that's undisrupted, let's say, compared to, it's a very unnatural situation compared to the century and a half before that. And so how this changes for structure, sorry, go ahead.
Yeah, so do you have a bias with trees that were in fact, like, that ultimately died from fires that were so bad that they killed the tree, and so the tree ring ends and maybe the tree rots and it's not in your sample?
Yeah, of course we can date the trees that are no longer there, right? So there are, but there is the fact that, you know, we find trees like this all over the place that have recorded these ground fires that were not killed, you know, 14 fires that were not killed by any of these fires is evidence that these fires were ground fires and not destructive fires. Yeah.
So I guess, so ultimately, I mean, it sounds like there's a bias, but you still capture the events from the trees that did survive the major fire. The ones that died, fine, you missed them. The ones that survived it, for whom that big fire wasn't just a brush fire, you do see that fire overall.
Yeah, but the thing with fires is it's unlikely to, you know, it's unlikely that it's kind of either a ground fire or a big destructive fire. You know, if a fire burns through a forest and it's a big destructive fire, you won't find 10 or 20 trees that have survived it and have recorded as a fire scar. Do you know what I mean? Then it's gone. And so there are forests like the boreal forest in Canada that naturally don't have this kind of fire regime where you have ground fires every 5 to 10 years or even every 20 years is typical for drier forests, such as the Mediterranean climate in California or drier forests throughout the American West. In colder forests like the boreal forest in Canada, you won't find these kind of fire scarred trees, or very few of them, because they have, the way the fire regime works there, they have a history of stand replacing fires, of fires that actually destroy the whole forest and then a new forest comes in, and those happen every 200 or 300 years. So it's a whole other fire system.
Okay, so then if there's a very severe fire that takes out a bunch of trees, how would you detect something like that? Is there other evidence?
Yeah, they can look into when a cohort of young trees comes in, when you date all the trees in a forest, or many of the trees in a forest, and they all date to having started growing within 10 or 20 years, you know that right before that some really big event happened in that forest that made space for these new trees to come in. And there's naturally, from natural causes, there's not that many disturbance factors that can cause these really big stand replacing events. And wildfires is one of the most evident ones. You know, a storm or a windfall will typically not destroy an entire forest or an entire state.
Right. No, that helps. Thank you.
Yeah, thank you. Good questions. As to fire, I think one way to show, to make it really visual, what the 100 years of fire suppression does to a forest, is this is a repeat photography project from my former advisor, my postdoc advisor. You know, the Sierra Nevada mountains were a popular tourist destination already in the early 20th century. And so this photograph that you see here is taken in 1923 in the Sierra Nevada forest. And what you see is a typical structure of a forest that is subject to these frequent ground fires, right? You can see two very distinct layers. You can see the mature trees And then you can see the underbrush and the grasses, and there's not much in between. It's a park-like, we call it a park-like forest structure. For your reference, there's a ranger standing here. So these are big, big mature trees. Alan, my colleague, went back to that same spot. So 75 years later in 1998, mind you, this is already almost 30 years ago, right? And this is what that forest looks like now after 75 years of fire suppression. So all of that underbrush, all of the saplings and seedlings have, instead of being burned off every 10 years, they now had 75 years to grow into actually, bigger trees. So you lose that that park-like or that two-story structure. And now your structure of a forest is kind of a continuum with mature trees, middle-sized trees, and then still some underbrush and grass. And now, of course, when a fire now hits this kind of forest, it won't be a ground fire because there's so much fuel, there's so much biomass on the landscape that it will not just stay to when a fire happens now, it will not stay just with the underbrush and the grasses. It will actually become so big that it will also reach the canopies of the mature trees. And that's the situation that we find ourselves in because we have so much biomass on the landscape. Now when a fire hits, it becomes a big destructive fire rather than an innocent ground fire. In addition to that, these middle-sized, 75, 100-year-old trees, they literally form a ladder. It's a ladder effect where these ground fires can now climb through this mid-sized canopy to reach the higher canopy. So as a result, of course, this fire suppression, this legacy of 100 years of fire suppression is not happening in a vacuum. It's happening while our droughts are getting hotter. And the longer fire season. So together that combines to see the destructive ground fires across the American West that we are experiencing. All right, I have one last topic I'd like to discuss if I have time for it. And this is
atmosphere. Let me ask you something about the tree rings. First of all, you pointed out that a more dense forest is more vulnerable to fire, obviously. What about things like forest carbon and biodiversity? Because eyeballing, this looks like a pretty healthy forest, a lot of trees, happy. It looks happy, right? So independent of fire, what is the state of these forests in terms of how they behave, how they grow?
You mean you're talking about the photo on the right here, or
Well, on the right, because it looks very dense and looks like a lot of species, which in some ways is good. I mean, ignoring fire, obviously. So what kind of forest are we looking at? Like, is it healthy in other dimensions? What's a good way of managing it?
Well, I mean, we know the solutions to this. I mean, it might be a healthy forest, but if the risk of it burning down, this is too dense to be honestly to be a healthy forest. This is not a natural state for the dry forests here in the American West. You don't want a forest to be. There's too much competition for nutrients, for water, obviously. So you don't want the forest. I mean, in terms of biodiversity, I think it's hard to tell from this one photo. It's also, I mean, the reason why these stand replacing fires are a big issue, not just obviously because they're dangerous and for us people and they destroy the forest. The problem is also that the species that come in after a stand is burned down, 1 year burning down 500, 800, 1,000-year-old trees that have survived there for so long. But two, because all of this is happening in a warmer, drier climate, the tree species that come in are not the same species, and many of them are invasive species. So you're creating a whole new forest ecosystem. But again, many of those are invasive species, so it's not a good thing for biodiversity either. And of course, in terms of carbon, you're right. I mean, this is you know, these young trees, they do store a lot of carbon, but when a fire hits, it burns it all. It's all gone up in you know, all goes back into the atmosphere in one fell swoop. So that's kind of what we've been seeing in Oregon, where a lot of forests were planted as part of carbon offset programs, but they've almost none of them are there anymore because they've all gone up in smoke, literally.
So then, I mean, let's say carbon offset, like that's a good example. So the right way of doing that, it sounds like, is more like a picture on the left. You get less carbon storage, but it's stable. Is kind of how
exactly. I mean, yeah, that's the issue with carbon offsets, and we see that in Europe as well. Not even only with carbon offsets, but with the with us counting on forests taking up much of the carbon dioxide that we put out, right? So, for instance, in the Paris Agreement, you know, we the countries that have agreed to limit climate warming to 2 degrees, to limit it by reducing their amount of carbon dioxide emissions. That reduction in the amount of carbon dioxide emissions, they count on the forests and the oceans taking up, you know, 30%, 50% of the carbon dioxide that they put out. But we're seeing that, one, with drought, trees die. Two, with wildfires, all of that, you know, wildfires put all of that carbon right back into the atmosphere. So actually the amount of carbon dioxide that forests can take up is diminishing much faster. And it's actually, that's a big area of research, not what I do necessarily, but is to look in, are forests still taking up more carbon than they are emitting? And we're really right there at the boundary. Even in countries like Sweden, Norway, they really count on their forests, very forested countries, count on their forests to take up CO2 emissions, but the forests are less able to do so because the climate is warming up, because it is drier, and because of these wildfires. So it's, yeah. Okay.
So actually, on this topic of climate change, currently forests are moving, well, north. So do you have records of that, for like ecosystem migration in the past data?
That's a colleague. I have colleagues who study that exactly, who kind of what I said earlier, who go to, you know, Arctic regions, polar regions, and look, and when the young trees, and they work with shrubs as well, when they established, and they go to the northernmost boundary and they look how long have these, you know, how long have these trees and shrubs been here. And so, yeah, you can look at how that movement happens. Yep.
Got it. Thank you very much. And actually, one more. So you've talked about based on tree growth, you infer what must have happened. Does the reverse hold also? By observing tree rings and how much the tree grows in various climates, assuming you do know the climate at the time, can you infer the growth patterns of a given tree under competition, under climate, you know, variations in weather, like make tree growth models based on these records?
Yes. Yeah. So that, again, that's not my field of expertise. And I also have to say, I kind of, I simplified things here a little bit. To move the story forward. But of course, climate is not the only thing that influences how much a tree grows in a certain year, and hence how wide its ring is. There is the geometry of a tree. There is the competition with other trees. So there are multiple factors, but so we have ways of dealing with that. We take, of course, multiple samples. We select the sites where we collect the samples and so forth. But depending on on the goal of what you're trying to achieve in your study, when you do climate reconstruction, you're going to go and sample different trees than when you want to indeed study how climate impacts a forest. So also, if you're looking at a forest stand, you will want to you will want to sample all the different species, not one
Yep.
particular species, and all of these things. So yeah, that's quite a big application of tree rings as well. As I mentioned, the study of forest history. And then my colleagues would do that. Of course, the one of the main goals is to see how will this collaborate with modelers, or put that in Earth system models to see how will this change in the future. And indeed, just what I mentioned, like how will our forests, how much carbon will they be able to uptake in the future, given what we know from the past.
Right. Thank you very much. Yeah, that's excellent.
Thank you. Okay, I'll try and be quick about the jet stream. This is a study we published recently, where we used the rings and trees to reconstruct the jet stream. So now not just climate on the Earth's surface, but the jet stream are the winds that blow about 6 miles above the Earth's surface in an eastward direction. They're driven by the Coriolis force of the Earth. They blow in an eastward direction. The jet stream is a reason why if you fly from the US to Europe, it's much faster than if you fly the other way around, because it's about the elevation that airplanes fly. And if you fly eastward, you get a tail jet stream wind. If you fly westward, you gotta make a big detour to avoid the jet stream. The reason why we're interested in the jet stream, one, is because even though it happens high above the Earth's surface, it really has an important impact on what happens at the Earth's surface weather-wise. So it's an important cause of climate extremes. And two, this is one of the components of the climate system that we don't know, unfortunately, well enough how it's going to react to anthropogenic climate change. So in climatological circles, there's a lot of debate about what's happening to the jet stream now and how this will evolve in the future. So we decided to use tree rings to see if we can reconstruct these winds that happen high above the Earth's surface, and so what we can learn from the past. We did the studies is over Europe. And you can think of the position of the jet stream, so how far north or south the jet stream is at, as the boundary between cold Arctic air and warm tropical air. And so when the jet stream is further north than normal, you get warm tropical air coming much further north than normal, and your cold Arctic air kind of being stuck, in this case, over Iceland. And so you get over Europe, you get nice and balmy summers in Belgium, where I'm from originally, and the UK. It's kind of what you see in the left-hand cartoon here. In normal years, the jet stream is located north of Scotland, and so you get warm air in summer over Western Europe. When the jet stream is positioned in summers where it's positioned further south than normal, you get the cool air from the Arctic coming much further south than normal. You get cool and wet summers over the UK and Western Europe. And then in contrast, the warm air from the tropics gets kind of stuck south of the jet stream, and so you get heat waves in the Balkans. This is what we call a dipole. It's a seesaw, basically, between the summer weather in northwestern Europe, in the UK and Ireland, versus in southeastern Europe, in the Balkans and Italy. And so I showed. Sorry, I left out one. I left out one slide. I'm sorry about it. Anyway, when you correlate that position of the jet stream, how far north or south it is, with temperature fields over Europe, summer temperature fields, you see that dipole here. So blue colors are negative correlations in northwestern Europe. The red colors are positive correlations in southeastern Europe. And so our hypothesis was, if we use tree rings from those two locations from the Balkans on one hand side and Scotland on the other hand side, if we use temperature sensitive tree rings from those locations and we combine them, we should, the only reason why, the only climatic pattern that causes this seesaw between temperatures in those two locations is the jet stream. So if we take tree rings from those two locations, we should, in theory, be able to reconstruct the jet stream. So that's what we did. I was smart in that I went to go do field work in Greece, which is on the right. They have gorgeous old trees, 1,000-year-old trees, beautiful landscapes, good weather, good food, good infrastructure, super friendly people, everything that one can dream of when one's doing field work. On the left, you see my colleagues in Scotland who were less lucky in terms of weather and food, and especially less lucky in terms of finding old trees. Because if you want to go back more than 400 years in time in Scotland, you cannot do it using living trees alone. There is no, the trees, the oldest living tree in Scotland is something like 400 years or so. So if you want to go further back in time, you got to do what you see them doing here, is to dive into one of the ice cold lakes and dive for subfossil wood. So these are trees that fell into the lakes over time, have been preserved because it's underwater and there's no oxygen. The wood can be preserved over hundreds of years. So you then dig up one of those stems, handsaw a cookie, as we call it, from that, send that back to the lab, tree ring date that cookie, and then hope that the tree fell into the lake not 20 years ago, but 200 years ago, so you can actually go further back in time. By doing that, they were able to develop an 800-year-long tree ring chronology from Scotland. Our chronology from Greece and Bulgaria and the Balkans was 800 years long as well. So by combining these two, we then combined the two. Then if you compare that to the jet stream position, is what you see here. This is now just over the instrumental period. A comparison, the orange line is instrumental measurements of how far north or south the jet stream was positioned each year from 1948 to now. The black line is our tree ring, combination of our tree ring records, and you can see that the black line tracks the orange line really well. So actually it works that we can use these tree rings from very specific locations to reconstruct patterns of the jet stream. And I do want to point out but this is quite remarkable, if I may say so myself, because what you're looking at here are tree rings through a microscope now. In order to get a temperature signal out of tree rings, for instance, in the Balkans, where really the width of the rings is mostly dependent on drought, not on temperature. So if you want to get a temperature signal, you need to get another measurement, another proxy from the tree ring data. And so what we did is we measured the density of the wood of each ring. And density is well known to be much more sensitive, a much better representation of summer temperature than the ring width. And when you measure the density of the wood, what you actually measure is the width of the cell walls, of individual cell walls. So what you're seeing here is a microscopic image, and I don't know if you can see, but what we did is we measured the thickness of the cell walls of the late wood, the wood that's formed in summer, from year to year, right? So some years it's thicker than other years, and that is determined to a large extent by summer temperature. And so we then compared these subcellular measurements to the jet stream, which is a phenomenon that covers the entire northern hemisphere at 6 miles above the Earth's surface. And it works, right? They are matched. They are correlated with each other. So that's, we were very happy with that result. We're then able to use that correlation, that relationship between our tree rings and our jet stream, instrumental jet stream record, to not just look over the instrumental period, but now to pull that reconstruction back 800 years to 1300, I guess 700 years, excuse me, to 1300 CE. And if you then look at the patterns over Europe over this period, you can keep seeing that dipolar, the contrast between Northwestern Europe and Southeastern Europe. So you can see it in the temperature, you can see it in the air pressure, you can see it in the drought, you can see it even in the precipitation and so forth. So it is a really consistent pattern that whenever Northwestern Europe is hotter and drier than normal, Southeastern Europe is wetter and colder than normal, and vice versa. And actually, this is where this is exactly what we experienced this past summer as well, where overall 2024 was the hottest summer on record in Europe. But when you look at the map of how the temperature is distributed, you see that it's especially over Southeastern Europe, over the Balkans and Italy, that all of that heat is concentrated. And then actually Northwestern Europe was slightly cooler than normal. So this pattern of caused by the jet stream, this contrast is superimposed on anthropogenic climate change. And it creates even hotter heat waves and hotter droughts in some areas whereas it might soften some of the global warming effects in other areas.
So can this be used to calibrate climate models? Because
Absolutely.
usually calibrate for a short history. This is a very long history for a climate model.
Yeah, that's exactly our aim, is exactly not just to understand what happened in the past, but to improve, to reduce the uncertainty of climate models that look at what's going to happen in the future, to make those more coherent. That's why we collaborate with climate modelers.
Okay.
One last thing, and then I'll leave it here, is that when working, the one cool thing about working in Europe is that we don't only have trees, but we also have long history of writing things down, of documenting many things, right? Of documenting weather conditions, of documenting harvest conditions, of documenting diseases, and so forth. And that is a field of science in and of itself. Environmental history is to extract information, climate information, environmental information from the centuries of documentary data. And what we did in this study is also compare our tree-based jet stream reconstruction and the extremes of it to things like grape harvest, grain harvest, wildfires, and epidemics that were recorded, so fully independent, that were recorded in the documented history. And this graph might be a bit confusing, but I'll try and keep it simple. Blue colors is what's going on in the British Isles. Red colors is what's happening in the Balkans and in Italy. On the left of the vertical black line is jet stream positions that are in further south than normal. On the right are jet stream positions that are further north than normal. And then we looked at grain prices on the top, grape harvest in the middle, and then wildfire and epidemics in the bottom row. And for instance, grape harvest, we don't have grape harvest for the British Isles, but we do have grape harvest data for the Balkans and Italy. And you can see that bad grape harvest, so happened during cold and wet summers, and it consistently happened when the jet stream was in a southern position, right? So you can see that red blobs occurring to the left of that central blue line. Central black line. Wildfires in the Balkans, on the other hand, happened when the jet stream was further north than normal over those past 700 years, and conditions were hot and dry. What was really unexpected for us was the clear link between plague outbreaks and the jet stream, where we can see that's the bottom right graph. We can see that plague outbreaks in red in the Balkans happened primarily when the jet stream was further south than normal and conditions were cold and wet there. Whereas in the British Isles, those are the blue blobs, they happened when a jet stream was further north than normal. Plague happened in the Balkans when the jet stream was south, but in the British Isles when the jet stream was north. And so that shows that this pattern, this contrast between those two areas of Europe has not only been consistent, has been consistently creating climate extremes, but has also had a strong trickle-down effect on human history in society and economics and demography in European history. So to wrap up, I hope I've been able to share with you that how trees can inform us about the past, the present, but also the future of not just our climate, but also ecosystems and human systems, and especially how the three are linked. And if you want to, if you still want more tree rings, I have written a broad audience book on this topic. It's called Tree Story. It has been translated in 7 languages, including in Spanish, if you prefer to read in that language. And it was published by Johns Hopkins University Press, and you can find it in most places where one finds books. So thank you very much for your attention.
Excellent. Well, thank you very much. This was a fascinating talk.
Thank you.
All right. Bye. Have a good day.
Thank you. Bye-bye.